Reactions in alkenes. Carbon-carbon double bond is a site of high electron density, or we know as nucleophilic site, becomes the site of electrophilic attack. Reactions of alkenes are mainly electrophilic addition reaction. The reactions in alkenes are hydrogenation, hydration, halogenation in inert solvent and in water, oxidation, hydrohalogenation, and ozonolysis. Hydrogenation is an addition of hydrogen gas in the presence of catalyst platinum, palladium, or nickel. So here we have the alkene compound, addition of hydrogen gas. One hydrogen atom will be added to each carbon in the presence of platinum or palladium catalyst or nickel catalyst. Halogenation in inert solvent. The reactants are alkene and halogen in the presence of inert solvent. The inert solvent can be dichloromethane, trichloromethane, or tetrachloromethane. The product must be vicinal dihalide. Vis means next to another, means the halogen attached to the carbon must be next to other halogen attached to another carbon. This is what vicinal means. So each halogen attached to each carbon involved in the carbon-carbon double bond. This is halogenation in inert solvent. Halogenation in water. The reactants are alkene, halogen in the presence of water molecule. The product is halohydrin. So alkenes react with halogen, here for example Cl2, in the presence of water. Only one halogen atom will be added to the carbon, one carbon, and another one carbon is OH group attached to that carbon, the OH group from the water. So this product is called halohydrin. Note that the halogen, here halogen, adds to the carbon that has greater number of hydrogen. So between these two carbon, you have to count which carbon has greater number of hydrogen attached to that carbon. The halogen will add to that carbon. The OH group will add to the carbon that has less number of hydrogen. Markovnikov's rule. In addition of H adds to an alkene, hydrogen atom adds to the carbon atom of double bond that already has greater number of hydrogen atom. That is Markovnikov's rule. So if you look at here, between these two carbon-carbon double bond, the carbon on the right has more hydrogen attached to it, 2 hydrogen. This carbon on the left has 1 hydrogen only attached to this carbon. So in addition of HX here is halogen. So if you want to add hydrogen attached to the halogen into the alkene, the hydrogen will be attached to carbon that already has high number of hydrogen. And then the halogen will be attached to the carbon that has less number of hydrogen. So X will be attached to this carbon and hydrogen will be attached to this carbon. This is Markovnikov's rule. Hydrohalogenation applies Markovnikov's rule. Alkene and haloalkane as the reactants. The product is alkyl halide. So here focus on carbon-carbon double bond, reacts with haloalkane, hydrogen and halogen atom. here, this hydrogen here will attach to the carbon on the right, because the carbon on the right here has high number of hydrogen. The carbon on the left here, we only focus on carbon-carbon double bond. The carbon on the left here has no hydrogen attached to it at all. So the Cl will attach to this carbon. This is the product of hydrohalogenation. Hydrogen attached to this carbon, Cl attached to this carbon. So this product here we call alkyl halide. The hydrohalogenation follow Markovnikov's rule. So here the example HX, X can be HBr or HCl. So hydrogen will be attached to carbon which has high number of hydrogen. This is the mechanism of hydrohalogenation. Step number 1, we start with the formation of carbocation and halide ion. We know that the alkene has high density of electron at the double bond, making the alkene nucleophile. So the double bond is the nucleophilic site. It will attack the hydrogen of the haloalkane, because this hydrogen is partially positive. The halogen here in the haloalkane, the halogen here is partially negative because it is more electronegative than hydrogen. So this hydrogen is the electrophilic site. So the nucleophile carbon-carbon double bond will attack the electrophilic site of the electrophile haloalkane. Forming the bond, use these two electrons. One single bond consists of two electrons. These two electrons are used to form bond with this hydrogen, and these two bonding electrons are used to transfer to the halogen, making this halogen have one more lone pair of electrons. And when one of the carbon form bond with the hydrogen, leaving another carbon as carbocation. So the product now is carbocation and halide ion. Step number 2, the halide ion now is negatively charged. This halide ion is nucleophile. So this nucleophile will attack the carbocation. The carbocation is the electrophilic site. So nucleophile halide ion will attack this carbon by using the lone pair, two electrons from one of its lone pair, form bond with this carbon, making the product C single bond halogen. So this is the halogenation, hydrohalogenation mechanism, because it adds hydrogen and halogen in the alkene. Anti-Markovnikov's addition, it occurs only when HBr is used in the presence of peroxide. H2O2 is an example of peroxide. CH3OCH3 is also an example of peroxide. When HBr is added to the alkene in the presence of any peroxide stated, the hydrogen atom will attach to the carbon which has less hydrogen. If Markovnikov, hydrogen will attach to the carbon with more hydrogen. But now anti-Markovnikov, when addition of HBr in the presence of peroxide, hydrogen will be added to the carbon that has less number of hydrogen, which is here. This carbon has only one hydrogen. The carbon on the right has two hydrogens. So hydrogen will be added to this carbon. This is anti-Markovnikov addition. This is the product. But if there is no peroxide, if you're still using HBr but no peroxide, it will follow Markovnikov's rule as usual. Next is hydration, electrophilic addition of water. Hydration is an example. So addition of water with catalyst dilute sulfuric acid or phosphoric acid, it follows Markovnikov's rule. So hydrogen is added to the carbon with more hydrogen number to produce alcohol. One hydrogen will attach to one carbon and OH group will attach to another carbon, and it has to follow Markovnikov's rule. The product is alcohol. Mechanism of hydration. First step is formation of carbocation. Alkene has nucleophilic site, the carbon-carbon double bond, electron-rich nucleophilic site. It will attack one of the hydrogen in the water acidic, because H2OH plus, okay, water acidic, because water in dilute H2SO4 or phosphoric acid. So that's why the carbon-carbon double bond will attack the water acidic. So H3O plus here, water acidic, H3O plus. One of the double bond will be used to form bond with the hydrogen here, with the hydrogen here, and these two electrons bonding OH, these two electrons will be transferred back to the oxygen here, because oxygen prefer to have two lone pairs of electron in water. So the products are water and carbocation. One of the carbon form bond with the hydrogen, another carbon will become carbocation, and the product is tertiary carbocation here. Tertiary carbocation, it follows Markovnikov's rule. The hydrogen here is added to the carbon which has high number of hydrogen already. So this carbon has two hydrogen, this carbon has no hydrogen at all. So this hydrogen will attach to this carbon, and this carbon will become the carbocation. So you call it as tertiary carbocation because it attached to three other carbons. So tertiary carbocation and water. Step number 2 is the formation of protonated alcohol. The water now, oxygen is the nucleophilic site because it is rich in electron. So the oxygen in water, it will use one of the lone pair to form bond with the carbon. So this lone pair attack the electrophilic site of the carbocation, form bond, making protonated alcohol. Protonated alcohol means OH group with one hydrogen. So this is protonated alcohol. And then we need to remove the proton by taking another water molecule to attack the proton in protonated alcohol. The lone pair will be used to form bond with hydrogen, because we need to eliminate the proton H+. So it will form bond with H, and then the bonding electron here will be transferred to the oxygen, because oxygen prefer to have two lone pairs here. Oxygen positive, oxygen does not prefer to be positive, it prefer to be negative. It prefer to have lone pair. So that's why this bonding electron transferred back to the oxygen. Now the product are alcohol and H3O+.